Good morning. Welcome to the conference Grip on Complexity. We have a lot of different speakers from Boston, although his plane didn't arrive, from Switzerland, and from all kinds of different science and industries. Today they're going to talk about the importance of complexity theory for all these different industries. And we're going to ask to the public, if we had 20 million euros, how would we basically invest that in different projects? Come and take a look.
The intention today is that we, together today, at the end of the day, create new ideas. And we tried to figure out what is this concept that we call complexity.
The power of the networks is really coming from the fact that not only that many complex systems have a network structure, but networks help us reveal the fact that systems that apparently have nothing to do with each other, like the cell, like the internet, like the social networks, have common organizing principles. So there is a common intellectual trust behind that, because it's really telling us that their organization is really shared between them. When we drive a car, we do not think about 5,000 components. If you are in Europe, having control over 4 components gives you full control over the car, which is the steering wheel, your gas pedal, your brake, and your clutch. And by changing the state of these 4 components, you can make the car to go from anywhere to anywhere. Now, of course, a car is controllable because it was built to be controllable. And I urge you not to buy a car that does not have that property that you can control it from these 4 components. That being said, what if I invert the problem? What if I start out from a wiring diagram of a car that I give it to you and say, could you find on this wiring diagram what are the 4 points from which you can control the car? And that is not an easy answer to that. And of course, if you know how the car is wired and you know much about cars, you may be able to find that. But you would say, why would I ask that question? And I would say the reason I ask that question is because this is a fundamental question in complex systems. And the answer was provided in a paper that we published about, and what we did in here is that we showed that the controllability problem can be solved to the degree that if you give us a directed network, we can identify who are the control nodes, which are the nodes through which you can actually control a system. And let me illustrate that in this organizational network. What was the problem with this organization? That is that why did the CEO and the management feel that they have a communication problem? Well, we can see that there are a few major hubs in the company. So you would think that through them, the news can actually spread. You would also hope, however, that the hubs are those who should be the hubs, which is the leadership. Well, let's see if that's the case. Well, here what I'm doing is I'm putting the different hierarchies on the network. The red nodes here in the middle are the directors and the CEO. And the bad news is that you don't see any hubs among the directors and the CEO. Now, let's go one level down. Top management. These are the blue guys here on the left. And unfortunately, we do not see any blue guys as a hub. If we look carefully, what we realize is that the hubs come from the bottom. The biggest hub is really an associate, this guy in the middle, who is in the lowest rank actually within the company. Yet, as I'm illustrating in this slide, he's about 2 links away from everybody within the organization.
If we don't make a major blunder, but with humankind you never know, if we don't make a major blunder by the end of this century, global poverty is over. This is going to change the world in ways uncomparable to anything that has happened in human history. We are getting richer, so the median is moving to the right, and the distribution gets skewed to the right. And that's the really important thing. These are hundreds of millions of people nowadays in China, India, Brazil, what have you, who already have the standard of living that we are used to here. Well, what you see is this looks like a complex, tightly coupled system, doesn't it? And Hastings says, we need a Harrison-May scaling in there if this is to be stable. But if we talk about money, there's no reason to expect this. If we talk about, oil and Philips products and stuff, it takes time to ship these things. And if you have more customers, you distribute, the fraction of your output that goes to each customer may become smaller and smaller. So that's this thing, you need to stabilize the thing. But we're talking about money here, in an era where money is just digits on a computer. So you can have huge transactions in nanoseconds, whatever, with very, very tight, strong couplings in this global financial network. Now, this year, a group led by Stefano Battiston and Guido Caldarelli is in this group, and Nobel Prize winning Joe Stiglitz is in this group, and guess who? Robert May is in this group. He's still around. They publish a paper, and they argue forcefully that we should simplify financial markets. This is after the crisis. And they say, connectivity of market players give rise to the conditions stipulated by the May-Wigner theorem.
I'm talking here with Carlo Jaeger, who gave a presentation about the possibility of green growth in relationship to complexity theory. How are these two connected?
They are connected because clearly with economic growth many things can go wrong, especially when it gets as huge as is happening right now. We have problems from climate change to air pollution to problems with pandemics, and to avoid the negative implications of growth, we have to deal with very complex situations. And if we don't understand a bit better these complex situations, growth will lead to what is called a normal accident and many normal accidents. And on the other hand, if we don't have economic growth on the planet in the coming decades, there's billions of people who will not accept this situation.
So what I will do is, after a short introduction in the world I daily live in, which is semiconductor industry equipment, and the company I work for, ASML, I want to share 3 cases. These are meant to stimulate discussion. And as in any brainstorm, there are no bad ideas, so I hope you would agree there are no bad cases, because any idea stimulates the new cases and new ideas. This is a measurement point, and at this point, for a given focus and dose, which we control, we know whether we have a defect or not. And as the system progresses, as more and more measurements come in, we get a better map of what this function is. So here in the vertical axis, you see the precision. You see how well this model, as we build it up, predicts whether or not I have a defect. So here I have only a 20% chance I make the right prediction, but as more and more measurements come in, so we now have 60 measurements, 80 measurements, you see that using this method, the model basically slowly but surely starts to come close to the real process. 99% of our work still consists of, you break down a complex system, you have an expert on lenses, you have an expert on stages, you have an expert on software. All these experts work in parallel in their projects, and we have found ways how to bring it all together. So, but this field really can, add to that. Having a different way of looking into our machine, having a different way to looking how we work, probably open up some mind. So we will probably become knowingly incompetent.
I'm very happy to talk here today about biological clocks. The title of my talks is Control of Our Biological Rhythms. And this is an experiment, a very old experiment, in which a human subject has isolated himself and sleep and wake was recorded. And what you see then is that the human being starts activity a little bit later every day and shifts to later times. And this is what we tend to do in the weekend. So especially adolescents have a tendency to go to bed late and to wake up late if they are allowed to. So this is a biological phenomenon.
Yeah, the lesson is that if you have problems with the biological clock, you don't necessarily have to look for a treatment aimed at a genetic or cellular level, but you may have to aim at a treatment at the level of the genetic, at the network level. Maybe you have to repair the network. Maybe you have to stimulate communication among the nerve cells within the network, because several diseases are clearly the result of a network problem rather than a cellular or genetic problem.
To summarize where I started with the important part, we have basically information and questions on 3 types of topics. One is on the complexity as a science, field of science. The second one basically dealing with questions around humanity's versus the sciences. This is complexity science, made the same when a physicist talks about complexity science or an economist. And number 3, basically all kinds of systems questions on applications of complexity into the system sciences, and also what is it doable.
And I think that was really important if you want to connect to social scientists, is that you offer a workable methodology. So that it's clear to the social scientists, you can't just come in with a model and say, here, this is a model, because that's not the way they are used to think. You need to explain how you identify the elements of a system, how you couple them, and how you study them.
And what happens when you make something really, really efficient, it can become brittle, because you've squeezed out all the redundancy and the learning power from the system. So there's a tension between something that's resilient and that's efficient.
And the question that we face today and that I was asked to address is, so how do you what's the application, what's the usefulness of complexity in the world of large business? So what I'd like to tell you about today is a project that I've been involved in as an external advisor. So I don't speak on behalf of the companies here, but as an external advisor. But I think it's an interesting story. It's an example of this friction, this interaction between the severely abstract but exciting and important concepts of complexity science and the real worlds of large companies who are trying to get stuff done. This idea of we're facing a more and more turbulent world, and that will require a different way of looking at things. And after some discussions, they chose this resilience lens of saying, well, let's take the concept of resilience and let's think of it as a lens, as a different lens of looking at the world. And of course, companies look at the world typically through an efficiency lens, right? How can we make things cheaper, more efficient? And looking at systems through a resilience lens is quite a fundamentally different way of thinking about them.
The great opportunity that complexity offers, it can unite, bring together people from very different disciplines that have never looked at each other's problems. And now they have a common denominator, which complexity is, which still has to be worked on, because sometimes we think that we are discussing the same thing, but we are meaning different things. Complexity can mean different things in different disciplines, but here we have a unifying framework which potentially can revolutionize the way different disciplines look at the same issue.
I said the assumption before the crisis was that you only need micro supervision, let me call it that way, only looking at individual institutions. Worldwide, the conclusion has been drawn up to the level of the G20, so even the politicians have subscribed to this conclusion that we need what are now called macroprudential policies. Macroprudential policies, or macroprudential supervision, which stands for looking at the financial system as a whole.
Compartmentalizing the economy into subsystems with relatively clear, let me say elegant, interfaces. And I would add that this is especially important in view of the financial system.
Yeah, the financial system you described as a highly complex, highly unstable structure by design.
It's going very well. We've had some very good speakers from the different sciences, social sciences, life sciences, and particularly mathematics, physical sciences. Because the question we asked ourselves in the beginning of the day is, let's dream. And the grand dream, Peter, was just assume, we would have 20 million euros. Assume we would have that. And we had 4 years of our valuable life, and we have all those bright complexity scientists. Where the hell would we spend it? Well, spending isn't difficult, but how do we make sure we get something out of it that will revolutionize the world?
Yeah, well, just a few personal observations. Obviously, the first question that you raised, if you had 20 million, would you spend it on complexity? The answer would probably be no, obviously.
I sort of got into it pretty harshly. We said, you need to come up with a good plan. And I think actually, and that was basically the rest of my comments, that complexity science is a crucial way of developing system analysis for grand social challenges. So if you talk about 20 million, you have to think about who is going to fund my research.
So what did you think of the conference?
I had a lot of fun and I loved Carlo Jäger.
Why?
Because he's really inspiring and he really gave me a new idea for thinking.
I think this conference, if you would ask me, who would you take to an island where there's nobody else, I would take this whole conference and lock myself in there for a month or 2 months or 3 months, I don't. I would be delighted.
Yeah. I think we got some common understanding that we share some common problems in very differently and apparently unrelated fields like the humanities and the exact sciences.
Great, absolutely mind-blowing, because it really puts together all the decisive criteria for formulating a policy.
We have come to the end of Grip on Complexity conference. We had a lot of talk, a lot of intense talk, and there were interesting bridges being built between different fields. There were people who said, hey, we need to talk together, we need to develop tools together, we need to develop research together because we have so much to share. And the Netherlands is a really good place to share and to basically include other people. And of course there were questions about funding. Where does the money come from and how are we going to divide it up? But I think today was a very good day for complexity. We started and we will continue.